Hello, and welcome to Boring Science to Sleep, a quiet place where science becomes slow, soft, and easy to drift through. Tonight, you're going to gently explore what you might see as you approach the speed of light, not to learn everything about relativity, but simply to notice how the universe might slowly change around you. Before you settle in, if you truly enjoy these calm journeys through interesting facts about science, you're welcome to like this video and subscribe, only if it feels right for you. And when you're ready, let me know in the comments where you're listening from and what time it is right now. It's always a quiet joy to imagine how many different places and peaceful moments are gathered here together. Now, dim the lights if you can, perhaps let a fan hum softly in the background, allow your body to become comfortable, and give yourself permission to do nothing for a while. There is nothing to solve, nothing to remember. You can simply listen, breathe gently, and drift with the spacecraft into the quiet darkness. And whenever you are ready, we can begin. You are sitting quietly inside a spacecraft. For a moment, nothing is moving. At least, nothing seems to be moving. Outside the window, Earth hangs in the darkness, blue and pale, surrounded by a thin veil of atmosphere, with the familiar continents resting beneath drifting clouds. From here, the planet looks almost impossibly peaceful. There is no sound from space itself, no wind against the hull, no rushing air, no distant roar of the stars. Only the soft hum of the spacecraft around you. A few quiet systems are operating somewhere behind the walls, small currents of electricity moving through hidden circuits, instruments keeping track of your position, your temperature, your oxygen, and all the ordinary things that allow you to simply remain here. You do not have to think about any of them. You are safe inside the spacecraft. There is nothing to do. And then, very gently, the engines begin to work. At first, you notice only a faint vibration beneath you. The spacecraft does not suddenly leap forward. There is no violent movement. Instead, there is a slow, steady pressure, almost like an invisible hand resting against your back, gradually becoming a little firmer as the spacecraft begins to accelerate away from Earth. You feel the seat beneath you. You feel the quiet push of the engines, and that is almost all you feel. This is one of the first strange things about traveling extremely fast. You do not directly feel speed. Your body does not have a special sense that tells you, now you are moving at 100 kilometers per hour, now you are moving at 1,000, now you are moving much faster still. What your body notices is a change in motion. It notices acceleration. If you were inside a perfectly smooth train with no windows, and another train passed silently beside you, you might not immediately know which train was moving and which one was still. In much the same way, inside your spacecraft, the enormous speed itself would not press against your skin. The gentle acceleration would. So you remain there, resting against the seat, while the spacecraft slowly gathers speed. Earth begins to become smaller. At first, you can still see the familiar shape of the continents. Then the planet becomes more like a blue sphere. Then smaller still. The moon, perhaps, is somewhere nearby, although your attention is beginning to drift toward the darkness ahead. The stars are still stars. They seem ordinary. For now, there is something wonderfully quiet about this first stage of the journey. You are moving faster and faster, but the universe does not announce it. There is no enormous sign in the sky, no sudden boundary, no visible line that separates ordinary motion from extraordinary motion. The spacecraft simply continues forward, and as you imagine going farther and faster, you might begin to think about how empty space really is. It is tempting to imagine the universe as completely empty, as though your spacecraft were traveling through an endless room containing nothing at all. But space is not perfectly empty. There are tiny grains of dust, scattered atoms, small pieces of material left behind by stars and planets, and other almost invisible fragments drifting through the enormous spaces between worlds. At ordinary spacecraft speeds, these particles may seem insignificant. At extraordinary speeds, they become something different. A tiny grain that would barely matter to you at rest could become a powerful impact when your spacecraft is moving toward it at an enormous relative speed. The particle does not need to be large, it only needs to meet you. And so, in our imagined spacecraft, you have protection around the hull, allowing you to continue drifting through the darkness. There is no need to worry about the individual particles. You simply notice the idea for a moment, and then let it pass. Because the larger story is not about dust, it is about light. You look forward again. The darkness is beginning to fill with stars. Some are brighter than others. Some are so distant that their light has been traveling for an unimaginable length of time before reaching your eyes. And even though you are moving through space, the stars do not immediately seem to rush toward you. They remain quiet, patient, distant. The spacecraft continues to accelerate. The pressure against your seat remains gentle. The hum of the engines continues. And somewhere far behind you, Earth is becoming smaller and smaller, its light spreading softly into the darkness. You might imagine turning around one last time. The planet is still there, still blue, still familiar, but it is already becoming a memory of a place you have left behind. Then you turn forward again. The stars wait in the darkness. At these speeds, you might expect the first great changes to happen to your body, but they do not. The more interesting changes will happen to the light arriving at your eyes, because when you move quickly enough, you begin to meet light in a different way. A star that once seemed to shine from one part of the sky may not remain there in quite the same place. Light arriving from the sides will begin to seem as though it is coming more from ahead. Very gradually, almost too gently to notice, the sky will begin to gather in the direction you are traveling. You do not see that transformation yet, not clearly, not here at the beginning. For now, you are simply traveling. The engines continue their quiet work. Earth continues to recede. The stars continue to shine. And the darkness ahead remains wide and calm, waiting patiently for you to move a little faster. So you settle back into the seat. You listen to the faint vibration beneath you. You let the distant Earth become smaller behind your eyes, and you watch the stars ahead without needing to understand them, because soon, as your motion becomes faster, something very subtle will happen to the light coming from those stars. The universe will not move, but your view of it will begin to change, and for now, that is all you need to know. You can simply drift there, quietly, while the spacecraft continues forward. You continue forward. The spacecraft is still quiet around you, and Earth is now far behind, no more than a small blue point suspended in the darkness. There is no road beneath you, no horizon, no familiar landscape passing outside the window, only the stars. They seem to surround you in every direction, scattered across the darkness with a kind of patient stillness. Some are directly ahead, others are far to the side, and some are behind you, although you would have to turn around to see them. For a while, nothing appears unusual. You are simply moving through a sky filled with distant lights. But as the spacecraft continues to accelerate, you begin to notice something very subtle. The stars ahead seem to be gathering, not because they are actually moving through space toward one another, and not because the universe itself has suddenly begun to rearrange its stars. It is your motion that is changing the way their light reaches you. You might imagine, for a moment, standing outside on a quiet day while rain falls gently from the sky. The rain is falling almost straight downward. If you stand still, the drops seem to come from above. But if you begin moving forward, something changes. The faster you move, the more the rain seems to arrive from in front of you. The rain has not decided to chase you. Its direction has not suddenly changed. You are simply moving through it. Your motion changes the direction from which the drops appear to reach you. Now, replace those falling drops with light. The comparison is only an image, but it gives you something simple to hold on to. Light is arriving from stars all around you, and as you move faster, the direction from which that light reaches your spacecraft begins to shift. Physicists call this relativistic aberration. You do not need to remember the name. You can simply watch what happens. The stars that were once spread widely across the sky begin to appear closer to the direction in front of you. The forward sky slowly gathers. It is as though the enormous dome of stars surrounding you is being gently drawn toward the nose of the spacecraft. At first, the change is almost invisible. Then, little by little, it becomes easier to imagine. The stars to your left seem less far to the side, the stars to your right seem to lean inward, and the region directly ahead becomes increasingly crowded with points of light. You continue accelerating. The spacecraft remains calm. There is still no dramatic sensation inside the cabin. Your body knows mostly about the gentle pressure of acceleration, but your eyes are beginning to experience something much stranger. The sky is becoming directional. Ahead feels different from behind. The universe is no longer appearing evenly spread around you. The light in front is becoming more concentrated, and behind you, the sky begins to feel wider and quieter. Imagine turning around. The stars there have not disappeared, but they seem farther apart. The darkness between them becomes more noticeable. The forward sky gathers light. The rear sky gives more of itself to darkness. It is a gradual transformation, almost like watching a very slow current move through a still body of water. Nothing happens suddenly. Nothing announces itself. The universe simply begins to look different. You turn forward again. There is something else to notice. The stars ahead are not only gathering toward the front, their light is also changing. As you move toward incoming light, you begin to meet more of its waves in a shorter amount of time. The light shifts toward shorter wavelengths. In simple language, the stars ahead can begin to look bluer and brighter. The stars behind you experience the opposite tendency. Their light is stretched toward longer wavelengths, becoming redder and dimmer. We will stay with that gently for now. You do not need to think about equations or measurements. You can simply imagine the color of the sky slowly changing with your motion. Blue ahead, redder behind, light gathering in front, darkness widening behind, and still, the stars themselves remain where they are. This is one of the quiet wonders of relativity. The universe does not have to physically rearrange itself for your view of it to change. Sometimes, all that changes is the way light reaches you. You continue moving. The spacecraft glides farther from Earth. The stars ahead become increasingly concentrated into a smaller region of your field of view. If you could somehow draw an enormous invisible circle around your entire sky, you would notice that more and more of its light seems to be gathering toward the front. It is not quite as though the universe is collapsing ahead of you. It is more like your window onto the universe is slowly narrowing in one direction. You can imagine an immense quiet net stretched across the darkness. The stars are points resting upon it. As your spacecraft moves faster, the pattern you see becomes increasingly concentrated toward the direction of travel. Again, this is only a way of imagining the changing perspective. The fabric of space is not literally becoming a bent net simply because you are moving quickly. Your view is changing because the paths of incoming light are being experienced from a new state of motion, and this distinction will become important later. For now, you simply watch. The engine hum remains low. The spacecraft continues forward. The stars continue shining. Ahead, their light gathers. Behind, the darkness grows wider. You might look at one particular star for a long time. It is still only a tiny point, quiet, distant, unaware of the spacecraft drifting toward it. Yet the light from that star has traveled across enormous distances before reaching you. And now your motion changes the direction in which that ancient light appears to enter your eyes. You are beginning to understand something without needing to name it. When you move through the universe at ordinary speeds, the sky seems almost fixed. When you move very quickly, the sky begins to reveal the motion of light itself, and the faster you travel, the more noticeable this becomes. You settle deeper into the seat. There is nothing you need to chase, nothing you need to calculate. You can simply watch the stars gather quietly ahead. And perhaps as you look back toward Earth, you begin to wonder about something even softer. If light takes time to travel from one place to another, then the Earth you see behind you is not quite the Earth of this moment. You are looking at light that left it earlier, and as you move farther away, that delay will grow. Soon, the blue planet behind you will begin to tell you an older and older story. For now, though, the spacecraft continues forward. The stars gather, the darkness remains still, and the light keeps arriving, carrying with it pieces of a universe that happened long before your eyes received them. You continue forward, quietly leaving Earth farther behind. The spacecraft is still moving through darkness, and the stars ahead continue to gather toward the direction of travel. For a while, you simply watch them. There is something peaceful about looking at a star when you know almost nothing about it. A tiny point of light appears in the darkness, and your eyes receive it as though the star were simply there, shining in front of you. But the light has traveled. It has crossed an enormous distance before reaching your window. And because light needs time to travel, every distant thing you see is also something from the past. You can let that idea remain very simple. When you look at the moon, you see it as it was a little earlier. When you look at the sun, you see sunlight that left the sun a little earlier. And when you look at a star many light years away, you are seeing light that began its journey many years before it reached you. The night sky is therefore filled with old light. It is almost like a quiet collection of memories, arriving one small beam at a time. You do not need to reach into the past. The past is already reaching you. It simply arrives as light. Now imagine turning around. Earth is still behind you. It is much smaller than before, and its blue light is faint against the darkness. You point a telescope toward it. At first, you might expect to see the Earth as it is at that exact moment, but you cannot. The light entering your telescope had to leave Earth before it could reach you. And now that you are moving farther away, the journey taken by that light becomes longer. You are watching Earth with a growing delay. The farther you travel, the older the light becomes by the time it reaches you. You might imagine watching a city somewhere on the planet. The buildings are there. The lights are there. People are moving through their ordinary lives. But the image reaching your telescope is no longer quite up to date. It is a message that has been traveling. A small piece of Earth's history is arriving late. And as your spacecraft continues accelerating, something else begins to happen. The rhythm of those arriving signals begins to change. The light from Earth becomes increasingly stretched toward longer wavelengths. In everyday language, it becomes redder. This is part of what physicists call the Doppler effect. You do not need to remember the name. You can simply imagine the blue Earth gradually taking on a softer, redder appearance as it recedes farther behind you. The light becomes weaker too, not because Earth has suddenly become less bright in its own surroundings, but because you are moving away, and the light reaching you is being received differently. You watch. The planet becomes quieter. Its colors fade toward the darkness. And if you could watch a clock on Earth through your telescope, its rhythm could appear increasingly slow. The seconds would seem to arrive farther apart. The world below would seem to move in slow motion. A person might raise a hand, and the movement would appear strangely gentle. A vehicle might cross a street, taking longer and longer in your distant view. The hands of a clock would seem to creep. Everything would look as though someone had quietly slowed the entire Earth. But there is an important distinction here. What you are seeing is the behavior of the light arriving at your spacecraft. You are not simply watching the physical passage of time on Earth through an ordinary window. The light itself has been traveling. The signals reaching you have been stretched and delayed by your changing motion and increasing distance. So you continue to watch an Earth that is, in a sense, becoming an older Earth, an Earth made of increasingly old light. And perhaps you begin to notice how strange that is. You are traveling away from home, yet the image of home seems to travel with you. Only it is not the home of the present moment. It is a succession of earlier moments, carried outward by light. The Earth you see now is an Earth from before, and farther away it will become an Earth from even earlier still. You turn your attention forward again. The stars there are different. You are moving toward their incoming light rather than away from it. And so their light experiences the opposite kind of change. The wavelengths become compressed. The light shifts toward blue. The stars ahead can appear brighter and more intense. It is as though you are meeting more of their arriving light along the way. Again, the stars themselves have not suddenly changed into something else. Their light is being received differently because of your motion. Behind you, the light stretches. Ahead, it compresses. Red behind, blue ahead. The spacecraft continues onward. The contrast becomes increasingly beautiful in your imagination. Behind you, the distant Earth rests in a quieter and softer region of the sky. Ahead, the stars gather together, their light becoming more concentrated toward the direction you are traveling. And somewhere between them is you, moving through a universe where light is never simply a picture. Every beam carries information. Every distant image carries a delay. Every star you see is a small message from another time. You might imagine that the entire universe is speaking very softly, but never all at once. Instead, each message arrives after its own journey. A star sends its light, a planet sends its light, Earth sends its light, and you receive each one only after the journey is complete. This is why the night sky can feel so deep. You are not looking at a single moment. You are looking across many moments at once. Some light began its journey only a little while ago. Some began much earlier. Some has traveled for thousands, millions, or even billions of years before finally reaching your eyes. And now, as your spacecraft moves faster, you are changing the way those ancient messages arrive. The forward sky becomes brighter. The rearward Earth becomes redder and slower. The stars continue to gather ahead. And beneath all of it, the spacecraft remains quiet. There is no need to hurry. You can simply watch the light arrive, one small wave after another, one distant moment after another. And as you drift farther from Earth, another question begins to emerge, almost without asking. If the light reaching you can make Earth appear to move slowly, then what happens when the difference is no longer only something your eyes see? What happens when time itself begins to pass differently for you? For now, you do not need the answer. You can simply remain here, floating quietly between the old light behind you and the approaching light ahead. The stars continue shining, Earth continues turning, and the light continues carrying the past gently across the darkness. You remain inside the quiet spacecraft. Earth is far behind you now, a small and distant point of light, and the stars ahead continue to gather gently toward the direction of travel. For a little while, you can simply remain there. The engines hum, the spacecraft moves, your breathing is slow. And somewhere behind you, light is carrying an older image of Earth across the darkness. You have already noticed something strange. From your distant view, the clocks on Earth can appear to move more slowly. But now, imagine putting the telescope away. Imagine that you are no longer looking at Earth through a distant window of light. Instead, imagine looking at the clock beside you. It is right there, close enough to touch. Its hands move normally. One moment passes, then another. Nothing about the clock seems unusual. Your own heartbeat continues. Your breathing continues. The spacecraft continues its quiet journey. From inside your own surroundings, time does not feel broken. It does not feel stretched. It does not feel slowed. Your own moments simply happen, and this is where relativity becomes especially gentle and strange. The difference is not that your clock is faulty. The difference is that your journey through space and time is different from the journey taken by the people who remained on Earth. You can imagine two clocks. One stays on Earth, the other travels with you. Both clocks begin together. Both are perfectly healthy clocks. Neither one is wrong, but as your spacecraft travels at extremely high speed, the paths followed by the two clocks through the universe are no longer the same. Physicists describe space and time together as spacetime. You do not need to imagine a complicated mathematical structure. Instead, imagine an enormous invisible landscape, extending through every place and every moment. You and the Earth are both moving through this landscape, but you are not following the same path. Earth continues along its familiar path around the Sun. Your spacecraft moves away, accelerates, changes direction, and perhaps one day turns around again. Two paths, two clocks, two experiences of elapsed time. This is what we call time dilation. The phrase can sound technical, but the idea can be held very simply. When two observers follow different paths through space-time, less time can pass for one than for the other. For you, the traveler, your own clock continues to feel completely normal. You do not sit inside the spacecraft watching your seconds become strangely stretched. You simply experience one moment after another. Perhaps you eat a meal. Perhaps you look through the window. Perhaps you sleep. Perhaps you wake and watch the stars. Your life continues at its ordinary rhythm. But when you compare your clock with a clock that remained on Earth, the two may no longer agree about how much time has passed. You might have experienced a relatively short journey. Earth might have experienced much more time, and the difference becomes especially meaningful when you imagine returning. So, after traveling for a long while, you gently turn the spacecraft around. The engines begin to work again. The stars slowly change their arrangement. The distant Earth begins to appear in front of you. At first it is only a tiny point, then a brighter point, then a small blue sphere. You are coming home. Your own clock has been quietly measuring the journey. Perhaps years have passed for you, but much more time may have passed for the people who remained on Earth. You approach. The planet grows. Clouds become visible. The familiar blue surface returns. And yet, when you finally arrive, Earth may not be exactly the Earth you remember, not because the planet has traveled somewhere else, not because your clock has malfunctioned, but because you and Earth have taken different paths through space-time. While you were away, Earth continued into its own future. People who stayed behind continued living their lives. Buildings changed, cities changed, generations passed, the stars continued burning. And all of that happened while your own clock measured a different amount of elapsed time. This is one of the quietest consequences of traveling close to the speed of light. You do not need to imagine a magical machine that stops time. Nothing stops. Your own time continues normally. The time experienced by people on Earth continues normally for them. But when the two journeys are compared, the amount of elapsed time can be different. And there is something deeply peaceful about the fact that neither observer has to be considered the one who is really experiencing time. Each traveler carries their own clock. Each clock measures the journey along its own path. There is no hidden master clock floating somewhere beyond the stars, waiting to announce the one true time for the entire universe. The universe does not seem to carry a single universal stopwatch. Instead, there are countless local moments, countless clocks, countless journeys, and each one quietly follows its own path. You can return to the spacecraft now. The imagined journey continues. Earth is still far ahead. The clock beside you is still ticking. One quiet moment follows another. The spacecraft remains weightless around you, and for a moment, you might look at your own hands. They look exactly as they always have. Your body does not feel as though it has entered some strange new kind of time. You are simply here, breathing, listening, watching the distant light. And yet, somewhere far away, another clock may already be measuring a different amount of time. That is the strange softness of relativity. The universe does not need to announce that time has changed. There is no sudden sound, no flash, no visible boundary. The difference simply accumulates, moment after moment, quietly, almost invisibly. And once you begin to think about time this way, another part of the journey becomes easier to imagine. If time can differ between paths, then perhaps distance can differ too. Perhaps the enormous space between you and a distant star is not quite as enormous from your own moving perspective. The stars ahead remain quiet. The spacecraft continues forward, and the distance between you and them waits patiently in the darkness, ready to become something a little stranger. You continue through the darkness. The clock beside you is still ticking quietly. Earth remains somewhere behind you, carrying on along its own path through time, while your spacecraft continues along another. Ahead, the stars are gathered into a smaller region of the sky. And now, as your speed becomes greater, you can begin to imagine something even stranger. The distance itself can become different. Think of a star far ahead. From Earth, perhaps it is unimaginably distant. You could describe the distance in light years, but even the number itself can feel too large to hold in your mind. 1,000 light years, 10,000, perhaps even farther. From the perspective of someone resting on Earth, that distance remains enormous. But you are no longer resting on Earth. You are moving, and in your own frame of reference, the distance along your direction of travel becomes shorter. Physicists call this length contraction. The phrase sounds technical, but the basic idea can be held gently. As your speed approaches the speed of light, distances measured along the direction in which you are moving become shorter from your perspective. You do not feel the universe squeezing around your spacecraft. There is no physical wall pressing inward. Nothing suddenly bends in the cabin. Your instruments simply measure a shorter distance between you and the destination. You can imagine the universe ahead of you as a very long, quiet fabric. At rest, the fabric stretches far into the distance, but as you move faster, the portion of that fabric lying along your direction of travel becomes shorter in your frame. The destination has not moved closer because the star suddenly decided to approach you. Instead, the distance between your present location and that destination is measured differently. And this gives you one of the most beautiful consequences of relativistic travel. A journey that takes an enormous amount of time for people on Earth can take much less time for the traveler. Imagine a destination thousands of light years away. From Earth, the journey might appear to require thousands of years, even if the spacecraft could travel extremely close to the speed of light. But for you, moving at that extraordinary speed, the distance in front of the spacecraft can be greatly reduced. The universe ahead becomes shorter, not because the stars are collapsing toward one another, not because space is being physically crushed into a small tunnel, but because distance, like time, depends upon the motion of the observer measuring it. You remain inside your quiet spacecraft. You look ahead. The stars are still distant, and yet, in your own measurements, the journey is becoming more manageable. You might travel for what feels like a relatively short portion of your life, while a vastly longer period passes on Earth. The thought is strange, but it is not magic. It is simply one of the ways space and time behave when motion becomes extreme. And now there is another question. If the distance really becomes shorter, why would your eyes not simply see every distant object squeezed into a smaller shape? You might imagine flying past a planet. From the perspective of someone measuring the planet while it moves relative to them, Its length along the direction of motion is contracted, so perhaps you expect to see a flattened planet, a shortened planet, a little sphere compressed from front to back. But your eyes do not receive an object all at once. Light needs time to travel. The light from the front of the planet begins its journey toward you. The light from the back begins its journey too. But those different pieces of light do not necessarily reach you at the same moment. Your eyes receive information from different parts of the planet that left those parts at different times, and this changes the appearance. The planet may not simply look flattened, it can appear rotated, almost as though you are seeing it from a slightly different angle. Physicists call this the Terrell-Penrose effect. Again, you do not need to remember the name, you can simply remember the image. You are moving quickly past a distant world. The world is physically affected by the relativistic measurement of its length, but the light arriving at your eyes tells a more complicated visual story. The front and the back are sending you different moments. You are not looking at the entire object frozen in one single instant. You are receiving a collection of light signals, each carrying information from a slightly different time, so the object can appear to turn rather than simply shrink. This is one of the quiet distinctions that makes near-light speed travel so difficult to imagine. What is physically measured is not always identical to what the eye appears to see. The universe can be shorter in one frame of reference, while still looking beautifully distorted rather than simply compressed. You continue past the imagined planet. For a moment, perhaps it seems to rotate gently in the darkness. Then it disappears behind you. The stars remain ahead, and the same idea continues on a much larger scale. The distance to a destination can be shorter for you, while the journey remains enormously long for someone who stays behind. You could cross distances that seem almost impossible from Earth and still experience a comparatively small amount of your own time. Your clock continues. Your breathing continues. Your body remains quietly inside the spacecraft. And outside, the enormous universe seems to have become smaller along your path. There is no sensation of the contraction itself. You simply measure the destination and find that it is not as far away in your frame as it was in Earth's. It is almost as though the universe has quietly folded a little of the distance in front of you, not enough to make the stars disappear, not enough to make space vanish, just enough to change what an enormous journey means. And perhaps this is the gentlest way to think about relativity. Time can become different, distance can become different, but neither one needs to announce the change. You simply move, you measure, you watch, and the universe gives you a slightly different answer depending on the path you take through it. Ahead, the stars continue to gather. Behind you, Earth continues its long journey through time, and somewhere between those two quiet directions, you continue drifting forward. The distance to the stars is becoming shorter, but the closer you come to the speed of light, the more unusual the sky becomes. The light ahead grows increasingly concentrated. The darkness behind grows deeper, and eventually, you begin to approach a boundary that no massive spacecraft can cross. For now, though, you can remain with the quieter thought. 1,000 light-years may be an enormous distance, but from the right moving perspective, even an enormous distance can become surprisingly small, and the stars, still shining softly ahead, seem just a little closer than they did before. You continue forward through the darkness. The stars ahead are now gathered more tightly than they were before. The spacecraft remains quiet. Your clock continues to tick beside you, and the distance ahead, although still immense, has become shorter in your own frame of reference. For a while, you simply watch. The universe seems to be changing around you without ever becoming noisy. There is no sudden wall, no visible boundary, no sign hanging in space to tell you that you are approaching something extraordinary. And yet, there is a limit ahead, a very quiet limit. The speed of light, you can imagine your spacecraft continuing to accelerate. The engines work gently and continuously. Your speed increases, then increases again and again. From the perspective of someone watching from Earth, your spacecraft is moving faster and faster through space. But there is something it can never quite do. It can never reach the speed of light, not if the spacecraft has mass, not if you, the people inside it, have mass, not if the engines continue working forever. You can approach the limit, you can come unimaginably close, but the final step remains unreachable. It is almost like walking toward a horizon that seems to remain just beyond your fingertips. You move closer, the horizon remains ahead. You move closer again. Still, there is another tiny distance between you and it. The reason is not that the engines suddenly stop working. The reason is deeper. As a massive spacecraft approaches the speed of light, adding more speed requires increasingly more energy. At ordinary speeds, adding a little more speed is relatively straightforward. But near the speed of light, the situation becomes increasingly extreme. Each additional increase becomes harder. The energy required rises dramatically, and reaching the exact speed of light would require an impossible amount of energy for anything with mass. So the spacecraft can continue approaching. It can become faster and faster, but the limit remains ahead. You do not need to imagine the equations behind this. There are no numbers to memorize. You can simply imagine the spacecraft approaching an invisible shoreline. The closer you come, the more difficult it becomes to move even a little farther toward it. The speed of light remains just beyond reach. And as you approach, the view outside becomes increasingly strange. The stars ahead continue gathering. The light arriving from the forward direction becomes increasingly concentrated. The sky that once surrounded you almost evenly begins to feel as though it is folding toward the front. More of the visible universe seems to gather into a smaller region ahead. The rearward sky becomes quieter, darker. The stars there become increasingly faint. You turn your attention behind you. Earth is now extremely distant. Its light has already been stretched and weakened. The planet is barely more than a memory of blue. You look at the stars surrounding it. They are still there, but their light is moving away from the direction in which you are traveling. To your eyes, the rear sky becomes increasingly dim. You turn forward again. The contrast is almost dreamlike. Ahead, light gathers. Behind, darkness expands. And the closer you move toward the speed of light, the more dramatic this difference becomes. You might imagine the entire sky slowly flowing toward a small opening in front of you. Again, nothing is physically rushing into that opening. The stars are not falling together. The universe itself is not collapsing. Your motion is changing the way their light reaches you. The sky is becoming concentrated because light from many different directions is increasingly received from directions closer to the path of your motion. This is the same gentle effect you noticed earlier, now becoming much stronger. And yet, even here, your own experience remains surprisingly calm. Inside the spacecraft, your clock still ticks normally. Your breathing still feels ordinary. The cabin remains your small, familiar world. You could reach toward the wall. You could close your eyes. You could listen to the quiet machinery. You would not feel yourself becoming almost light. There is no physical sensation that announces your exact speed. Your extraordinary motion is revealed mainly when you compare your journey with distant observers and when you watch what happens to the light around you. The universe tells you through its appearance. The forward sky becomes brighter and more concentrated. The rear sky becomes darker. Distances along your direction of travel become shorter in your frame, and the difference between your elapsed time and the time experienced on Earth becomes increasingly large. All of these changes are connected. They are different quiet faces of the same underlying structure of relativity. You continue accelerating. The speed grows closer to the limit, but the limit remains, and there is something strangely peaceful about that. The universe does not need to allow everything. Some boundaries are built into the way space and time work, Light can travel at its own universal speed. A massive spacecraft can approach that speed, but it cannot simply become light. There is no final moment when you cross over and begin traveling at the speed of light. There is only the endless approach. Closer, 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 without arrival. You might wonder what would happen if you kept accelerating forever. Would the stars eventually disappear? Would the entire sky become a single brilliant point? Would the darkness behind you become complete? The answer is not quite as simple as a single picture. The sky would become extremely distorted, and light from the forward direction would become increasingly concentrated and energetic. But the spacecraft itself would still never cross the boundary. You would remain a massive traveler, always approaching, never arriving. And perhaps this is one of the gentlest lessons hidden inside the strange world of relativity. Sometimes the most important destination is not something you reach. It is a limit that changes everything as you approach it. You remain there for a moment, floating quietly inside the spacecraft. Ahead, the stars gather into their increasingly concentrated region of light. Behind you, Earth is almost lost within the darkness. Your clock continues, the engines continue, your journey continues, but the speed of light remains just beyond you, silent and unreachable. And as you rest with that thought, another possibility begins to appear in the distance. If you cannot move through space faster than light, perhaps there might be another way to change the journey. Perhaps, instead of making the spacecraft move faster through space, you could imagine changing space itself, not pushing the spacecraft through the universe, but changing the universe around the spacecraft. It is only an idea, a mathematical possibility, a quiet thought at the edge of what physics allows us to imagine. And somewhere ahead, in the darkness, the shape of that idea begins to take form. You have reached the quiet boundary. The spacecraft continues to approach the speed of light, but the boundary itself remains untouched. Closer, closer, never quite there. And now, instead of asking how you might push the spacecraft faster, imagine asking a different question. What if the spacecraft did not have to move through space in the ordinary way at all? You remain inside the cabin. The engines are quiet. The stars are gathered ahead. And for a moment, everything outside becomes still. Then imagine that space itself could change. Not the spacecraft, not your body, not even the stars. Space. The vast, quiet space surrounding you. In Einstein's theory of general relativity, space and time are not simply an empty stage where everything else happens. They can bend, they can stretch, they can change their shape in response to matter and energy. You can think of spacetime as the invisible structure in which your entire journey takes place. It is not a physical fabric you could touch with your hands, but it is a useful way to imagine the geometry of the universe. And if that geometry can change, perhaps you can imagine something even stranger. A bubble, a region of altered spacetime surrounding your spacecraft. Inside the bubble, you remain relatively calm. The spacecraft itself does not have to race through space at a speed greater than light. Instead, the space around the spacecraft would be arranged differently, so that the bubble itself could move from one region of the universe to another in a way that appears faster than light to an outside observer. This is the basic idea behind a warp drive. The name sounds almost like something from science fiction, and in many ways it is, because although mathematical models can describe such a possibility, there is currently no known practical way to build one. The idea remains speculative. You can simply let it remain that way. A thought experiment, a quiet mathematical landscape, something to imagine rather than something to prepare for. In this imagined journey, you are not pressing harder and harder on the engines. You are not trying to catch light. Instead, you are sitting almost peacefully inside a bubble of altered space-time. The spacecraft rests inside, and the bubble carries you. It is almost like floating on a very slow wave, except the wave is not made of water. It is made of the geometry of space itself. The space ahead would be arranged differently from the space behind. The bubble could, in the mathematical picture, move across enormous distances, while the spacecraft inside remains locally protected from the extreme motion. Again, you do not need to imagine yourself feeling anything dramatic. Inside the bubble, your surroundings could remain remarkably ordinary. You could sit in your seat. You could look at the instruments. You could breathe. You could close your eyes. The unusual part would be outside. And if someone far away could watch the bubble pass through space, the scene might become very strange. The bubble could appear to arrive from nowhere, not because it had literally appeared from nothing, but because its movement through space-time could be so different from ordinary motion that an observer would not experience the approach in the familiar way. The light around it would also behave differently. The curvature of space-time could change the paths taken by light rays. Light that would normally travel in a straight path could instead be redirected around the region of altered space-time. From far away, the bubble could therefore resemble a moving gravitational lens. A lens in space does not need to be made of glass. Gravity itself can bend the paths of light. A massive object can change the geometry around it, and light passing through that region can follow a curved route. A warp bubble, in this imagined situation, could create a similarly strange visual effect. You might see light from the distant universe bending around the bubble. Some of that light could seem to move toward one side, some toward another. The image of the sky could become divided into unusual paths, almost as though the universe were being reflected around an invisible shape. And yet, there would be no solid object there to create the effect. Only altered space-time. You can imagine looking at the bubble from far away. Perhaps the stars behind it appear displaced. Perhaps their light seems to gather around its edges. Perhaps the background sky becomes distorted into a moving pattern. The bubble itself might remain difficult to see directly. Instead, you would notice what it does to everything around it. The stars, the light, the darkness, the paths between them. It would be like watching a quiet disturbance move across an otherwise still night sky. But there is an important reason we must keep this part of the journey imaginary. A practical warp drive is not something modern science knows how to construct. Some mathematical warp drive models require unusual forms of energy, including regions of negative energy density. Older descriptions sometimes speak loosely of negative mass, but the more precise idea involves exotic distributions of energy in space-time. There is no known material we can simply collect and place around a spacecraft to create such a bubble, so the warp drive remains a theoretical possibility explored through mathematics, not a functioning spacecraft waiting in a laboratory. You can let that distinction settle softly. Everything you have experienced so far has belonged to established relativity, the changing appearance of starlight, the difference between elapsed times, the contraction of measured distances, the impossibility of accelerating a massive object all the way to light speed. These are parts of well-tested physics. The warp bubble is different. It is a speculative extension of what the mathematics of space-time might allow. And perhaps that is what makes it interesting. Not because it promises a destination, but because it gives you another way to imagine the universe. You are no longer the traveler forcing your way through space. You are the quiet passenger inside a region of space-time that is carrying you. The stars remain distant. The spacecraft remains calm. The bubble moves. And somewhere outside, light bends gently around its changing geometry. You remain inside, listening to the faint hum of the cabin. For a moment, you might imagine looking forward through the window. The stars are no longer simply stars. Their light has become part of the shape of the journey itself. And if the bubble could truly move faster than light, then the view from inside would become stranger still. Some light from the universe might be unable to reach you. Some regions of the sky might become hidden. Some parts of the cosmos could slip permanently beyond your view. So you remain quietly inside the imagined bubble, surrounded by a universe whose light is beginning to take unfamiliar paths. There is no need to rush toward the answer. The darkness can remain dark, the stars can remain distant, and the strange bubble can simply drift onward, carrying you through a version of space-time that exists, for now, only in the mathematics of imagination. You are still inside the imagined bubble. The spacecraft is quiet around you. There is almost nothing to feel. No great force presses against your body. No violent motion shakes the cabin. The instruments remain calm. The walls remain still. And yet, outside the window, the universe has become something unfamiliar. The stars are no longer spread across the sky in the ordinary way. Their light has been disturbed by the shape of space-time around you. Some rays of light that would normally pass directly toward your eyes may now curve around the bubble. Others may arrive from unexpected directions. The sky could appear stretched, folded, or gathered into unusual regions. You look forward. A concentration of light seems to rest somewhere ahead. You look to the side. The stars there appear displaced. And behind you, the darkness is deeper than before. It is important to remember that this is an imagined view. There is no experimentally confirmed picture of what a human traveler would see from inside a working warp drive. The mathematics can suggest unusual behavior, but the actual appearance would depend on details of the space-time geometry, the way the bubble was created, how it moved, and how light interacted with it. So you do not need to picture one exact scene. You can simply let the sky become strange, softly strange, almost dreamlike. Imagine light traveling from a distant galaxy. For billions of years, perhaps, that light has been crossing the universe. Then it reaches the region around your hypothetical bubble. Instead of continuing along the path you might expect, its route is altered by the geometry surrounding you. The light bends. It follows another path. Perhaps some of it reaches you from one side. Perhaps some arrives from another. And perhaps the same distant region of the universe can appear in a place in the sky where you would never have expected to see it. This is similar in spirit to gravitational lensing, where the presence of matter changes the geometry around it and causes light to follow curved paths. A distant galaxy can therefore appear displaced, stretched, or multiplied. Inside your imagined warp bubble, the geometry could create another kind of visual distortion. The universe around you would not necessarily look like a normal star field, moving quickly past a window. Instead, the light itself would become part of the strange landscape. You continue drifting. The spacecraft remains almost weightless. There is no need to understand every path taken by every photon. You can simply watch the light gather and bend. Somewhere ahead, a region of intense brightness seems to form. Beyond it, darkness. And somewhere within that darkness may be something even stranger. A region of the universe whose light cannot reach you. If the warp bubble moves through space-time in the hypothetical way these models describe, there can be regions from which light cannot catch up to the bubble in the ordinary manner. The travelers could therefore have a permanent invisible region behind their journey, not because the universe has disappeared, not because the stars have stopped shining. They may still be there. Their light may simply be unable to reach you. You could look toward that region forever and see nothing. The darkness would not mean emptiness. It would mean absence of information, and perhaps that is one of the most beautiful things to remember about the night sky. Everything you see is something whose light has successfully reached you. Every star is visible because its light found a path to your eyes. Every distant galaxy is present in your awareness because photons carried information across space and time. If those paths are interrupted, altered, or unable to catch up with you, the universe can become invisible without becoming empty. You remain inside the quiet bubble. The hidden region stays beyond your view. The stars that can reach you continue to glow, and the spacecraft continues moving through the imagined geometry of space-time. You might wonder what an observer far away would see. Perhaps the bubble would appear as a moving distortion in the background sky. Stars could seem to shift around it. Light could brighten along certain edges. The bubble might resemble a moving lens, bending the appearance of everything behind it. And perhaps, from one perspective, the bubble could seem to appear and disappear in ways that would be impossible to interpret using ordinary motion alone. But from inside, your experience could remain strangely peaceful. You are simply carried along. There is no sensation of racing through the stars, no wind, no sound, no visible motion like a landscape passing outside a train, only the changing arrangement of light. And perhaps that is what makes the idea of faster-than-light travel so different from ordinary travel. You are no longer imagining yourself as a traveler crossing space faster and faster. You are imagining space itself changing around you. Still, the universe does not give up its secrets easily. The warp drive remains hypothetical. The required energy conditions remain uncertain and deeply problematic. There is no known technology capable of creating such a bubble. There is no demonstrated method for controlling space-time in this way, and there is no confirmed way to send a spacecraft beyond the speed of light. So the journey you have imagined remains where it belongs, at the quiet boundary between established physics and speculation. Everything before this point began with things we know. You accelerated. You watched the stars gather toward the front. You watched distant Earth become older and redder. You imagined time passing differently for travelers and people who stayed behind. You imagined enormous distances becoming shorter in the traveler's frame. You approached the speed of light, knowing you could never quite reach it. And then, only after reaching that boundary, you allowed yourself to imagine another possibility. A bubble, a distortion, a different way of moving through space-time. Now the bubble can become quiet. The strange stars can fade. The distorted light can soften. The invisible region can remain invisible, and you can slowly return your attention to the spacecraft itself, the quiet cabin, the gentle hum, the steady rhythm of your breathing. There is nothing left to calculate, nothing left to chase. The universe will continue without needing your attention. The stars will keep shining. Earth will continue turning. Light will continue traveling through the darkness. And somewhere, unimaginably far away, galaxies will continue drifting through the vastness. You can let your eyes close. You can let the spacecraft become only a quiet room around you. The speed of light can remain far away. The stars can remain distant. The universe can remain wonderfully unfinished. And you can simply rest. And so, our journey drifts quietly to its end. Whether you're still listening beneath the glow of your screen, or already floating somewhere between dreams and distant stars, thank you for traveling here tonight, through silent galaxies, ancient light, changing time, and the quiet geometry of the universe. If this wandering brought you a little calm, you're welcome to subscribe or share it with someone who could use a gentler night beneath the cosmos. For now, rest well. The stars will keep burning. The planets will keep turning. Light will keep crossing the darkness. And the universe will carry on softly around you while you sleep. And so, the journey slowly becomes quiet again. The spacecraft continues to drift through the darkness, no longer needing to accelerate, no longer needing to chase the distant limit of light. Behind you, Earth is only a small point of ancient blue light, carrying with it the memories of everything you once knew. Ahead of you, the stars remain gathered in the distance, their light softened now, no longer something you need to follow. You have traveled through a universe where light can change the way the sky appears, where time can pass differently along different journeys, where enormous distances can become shorter for a traveler moving close to light speed, and where the boundary of light remains forever just beyond the reach of anything with mass. And then, for a moment, you imagine something even stranger, a quiet bubble of space-time, a place where you did not have to push yourself faster and faster, but simply allowed the geometry of the universe to carry you. It remains only an idea, a mathematical possibility, resting somewhere between what we understand and what we can still imagine. You do not need to decide whether such a journey will ever be possible. You can simply let the thought drift away. The universe is large enough for unanswered questions. There are distant galaxies whose light has been traveling for billions of years. There are stars whose ancient photons are only now reaching you. There are regions of space you may never see, simply because their light cannot reach your particular place in the universe. And there are still countless things that remain unknown. You can let all of that remain comfortably unfinished. For now, you are back inside the quiet spacecraft. The cabin is dim, the instruments glow softly, the faint vibration of the machinery surrounds you. Your breathing is slow. There is nothing to calculate, nothing to understand perfectly, nothing you need to remember when you wake. You can simply rest. Perhaps you imagine the stars outside becoming softer and softer, until they are no longer individual points, but only a quiet field of distant light. Perhaps Earth is somewhere behind you, turning peacefully beneath its clouds. Perhaps the spacecraft is floating between worlds, carried gently through the darkness. And perhaps, somewhere far beyond what you can see, light continues traveling through the universe, crossing distances so immense that your mind does not need to measure them. It only needs to wonder. So let your attention become lighter now. Let the distant stars remain distant. Let the darkness become comfortable. Let the spacecraft become still. You are safe. There is nothing to do. You can simply listen and drift. The speed of light can remain far away. Time can continue quietly. Space can remain wide and open. And the universe can carry on without asking anything from you. The stars will keep shining. The planets will keep turning. Light will keep crossing the darkness. And somewhere, in that enormous quiet, the universe will continue changing slowly, gently, endlessly, while you rest. For tonight, you have traveled far enough. You can close your eyes now and simply drift. Rest well. The universe will keep moving softly around you while you sleep.